Alright, welcome everybody to another Calcaholic video. If you're clicking on this video, you're here to find out everything there is to know about derivatives, everything to get you started on differential calculus. And if you want to know what a derivative is, well, you obviously have to ask the question, what is a derivative? Alright, and what is the answer to this? Well, my shortest answer will be that derivatives explain change. And by change, of course, we mean rate of change, could be slope, could be rise over run. All those things should ring a bell. So knowing that, let's look at these two linear functions here, y equals x and y equals 2x. Me being an expert mathematician, I'll tell you that y equals x has a slope of 1 and y equals 2x has a slope of 2. But how did we get there? So let's do some review. Finding change using rise over run. Again, here's the curve or the linear function y equals x. And let's call m our slope of this function. We're going to calculate that by getting the change, the net change of y, and dividing that by the net change in x. And of course, we'll do that by selecting 2 points. We'll define one to be p1 and the second one to be p2. And we'll follow the formula here for rise over run, and through some rigorous calculations get that our slope is equal to 1. Furthermore, we can look at a table here of input and output values. We'll see that when x is equal to 0, our y is equal to 0. When x is equal to 1, our y is equal to 1. When x is equal to 2, our y is equal to 2. So you'll see that every single time x increases by an increment of 1 unit, our y is increasing by an increment of 1 unit. So that means that our change, or the rise of our run, or the slope that we're seeing here is obviously 1. So let's put that to the side. Let's look at the linear function y equals 2x now. Let's look at that table of input and output values. For x equals 0, y is 0. For x equals 1, y is 2. For x equals 2, y is 4. So now, what about now? When our x changes by an increment of 1, our y is changing by an increment of 2. Obviously, we're going from 0 to 2 to 4. Those are differences of 2, so our slope is going to be 2 for this function. Alright, so that was rise over run, delta y over delta x. What about using slope-intercept form? And of course, this is our slope-intercept form, and I'm going to manipulate it a little bit. You can throw the b on the other side by adding on both sides of the equation, and we can set a to 0, so we're essentially saying that there's no horizontal shifts on the line y. And we get y equals mx plus b, and that's the very familiar equation that we've seen like way back when. So let's take y equals mx plus b and put it in the corner over here. And let's look at our graph of the linear function y equals 2x. And let's just compare that equation to y equals mx plus b. Just through observation alone and no calculations, we can clearly see that m is 2 and b is 0. And since m is our slope in this equation, that we can conclude that the slope of that was 2. Alright, but now let's ask, how do we find the slope of a curve? We were only looking at linear functions. What about non-linear functions? And just so we're all on the same page, this is a curve, this is a curve, this is a curve, this is a curve, this is a special curve, and this is a curve. Okay, so knowing that, let's ask the question, what is the slope of f of x equal to x squared at the point 1, 1? Alright, so let's pick 2 points. Let's pick 1 point, or point 1, to be a point that is 1 unit to the left of the point we're looking for, and then another point 1 unit to the right of the point we're looking for. And then what we'll do after is draw a line that intersects the function at only these 2 points, and then do rise over run on that line. Alright, and that's how we'll get an estimation for the slope at 1. But what if we want a more accurate representation of the slope? What we can do, and I'm going to run that animation again, is take x and f of x, or point 1, really close to point 2, and again draw that line, and take the slope of that line with the same formula. Alright, so TW warning, we're using numbers. So let's assume in this situation, for the 2 points that we pick, P1, x comma f of x, and point 2, a comma f of a, we're going to say that a is equal to 1 and x is equal to 0.999. Alright, well, we know the function is x squared, so let's go ahead and square both of those. We're going to get f of a is equal to 1, again, obviously, because 1 is, when squared is also 1. And then f of x is going to equal 0.998001. So let's pull that delta y over delta x formula out and then plug in our values and simplify. I'm not going to read all that, but simplified is 0.002 over 0.001. Simplified again, you'll get 2 over 1. Simplified even more, you'll just get 2. So we're getting that the slope is approximately equal to 2, right? Alright, like I just said, the slope of f of x equals x squared at the point 1 comma 1 is approximately equal to 2. But the problem here is we're still getting an estimation. This is a guess. We don't want an estimation. So what do we do? How do we avoid these approximations? Well, there is one way. We need to get x so close to a such that x essentially equals a. And this might not make sense because if we do take x to be a, we'll get 0 over 0. And of course 0 over 0 is bogus, it doesn't mean anything, so this doesn't make sense. Well, how do we explain this using correct notation? Because x can't equal a. Well, what we need to do is take the limit as x approaches a for f of x minus f of a over x minus a, for the difference quotient. And this is one of the limit definitions of a derivative. And if you're unfamiliar with what a limit is, please go ahead to our video about discontinuities and limits. It's in the AP Calculus AB preview. It's a really helpful video to get you started on that. Alright, well, before we continue, I want you guys to look at a secant line versus a tangent line, or the average rate of change versus the instantaneous rate of change. So this graph here is from the problem we looked at before, where we picked 2 points and drew a line. This is a secant line. A secant line crosses through the function at only 2 points, 2 and only 2. The slope of the secant line is called the average rate of change, and the formula for the slope of a secant line is delta y over delta x equals f of x minus f of a over x minus a. Alright, so what about a tangent line? Well, a tangent line is a line that touches the function at only 1 point. So your technical 2 points are the same point here, but they obviously can't be the same point, because if they were, then you'd have 0 over 0. Moving on, the slope of the tangent line is called the instantaneous rate of change. So it's not an average anymore. It actually is the rate of change at that point. Hence why it's called the instantaneous rate of change. The formula for the slope of a tangent line is dy over dx is equal to the limit as x approaches a for f of x minus f of a over x minus a. If you guys are paying attention, you'll see that dy over dx is used. What is dy over dx? Well, let's recall we know that delta y over delta x gives the slope of a secant line, telling us how y changes with respect to x. And what respect to x just means is like, how does y change when x changes? It's like the tables we were looking at before. How does y change when x changes? That's analogous to saying, how does y change with respect to x? Just so we're all on the same page. So then, if that's true, we're saying that dy over dx gives the slope of a tangent line, also telling us how y changes with respect to x. Again, how the input value affects the output value. Alright, if we're still confused, no worries. Let's look at the question we used earlier, the example, and let's just focus at delta y over delta x is equal to 0.002 over 0.001. Alright, let's move that to the corner, and let's just isolate delta y. So looking at this fraction, we can say that delta y is proportional to 0.002. And if that's true, we can imagine dy as 0.0 with an infinite amount of zeros in between the first and the last zero. So I know technically that doesn't make sense. How can you have an infinite amount of zeros but it has an end, right? But that's how we imagine dy. It's such a small number, but it just isn't quite 0. So let's look at delta x. We have 0.001 here. Again, dx is going to be an infinite amount of zeros in between the first and the last zero, so it's basically 0. So if we put dy and dx on top of each other, what do you think is going to happen? Well, they're two values that are really close to 0, but again, they're not 0. So you put them on top of each other, and you will get an actual finite value. In this case, it's 2. So let's just review or digest some of the notation that might be confusing you. Alright, so dy over dx here. Y prime and f prime of x are all describing the same thing. These are ways you would write the derivative, or in other words, the slope of a function. Okay, and I'll explain more, but dy over dx is pretty much the same as delta y over delta x. Y prime is telling you the slope of y, and f prime is telling you the slope of x. Alright, so let's look at the notation a little bit deeper. So for a function f of x equals x, prime of x just means the slope of the function f of x. Alright, similarly, if y equals x, the slope of y is 1, because that graph always has a slope of 1. And then dy over dx is the same as delta y over delta x, but for this curve, it will also be 1. So let's look at some more notation. So if we have a equation here, y equals x, and we're taking the slope of y with respect to x, well, we know that the slope of y is always 1, because for every time that x increases by 1, the y increases by 1. So dy over dx, or the slope of y with respect to x, is always 1. So now what if we wanted to take the slope of dy over dx, meaning that we're taking the slope of the function? Well, if you graph dy over dx equals 1 on a Cartesian plane, so a y and x-axis, it'll just be the horizontal line y equals 1. And that horizontal line has no change. It's constant. It's always 1, no matter where you are on the domain. So that means that the slope of dy over dx equals 1 is 0. And you would write that as d squared y over dx squared. So that notation just means the second slope of y, basically. Alright, but what about this over here if you're looking? D over dx. This is not a fraction. Dy over dx can be looked at as a fraction. This over here can be looked at as a fraction, but this is not. D over dx means taking the derivative. It's a verb. It's an operator. It's the same as multiplying, dividing, raising to a power, the square root, whatever you can think of, exponent. It's similar to that. It's an operation. It is not a number. So when I say d over dx of y or d dx of y, I'm saying you're taking the derivative of y, and that is equaling the slope of y or the change in y with respect to x. So that's what this reads here. All right. So how can we compute derivatives using the limit definition now that you're familiar with all the notation? So here's the difference quotient limit definition. It's the same as what we were looking earlier. So let's say we have the function f of x equals x squared. All right, and we want to know the slope of x squared. We need to take this limit. So let's go ahead and apply the limit. Using that notation on the left hand side, we're saying that the slope of the function x, or sorry, the slope of the function f is equal to the limit as h approaches 0 of x plus h squared minus x squared over h. Alright, so how do we go about this? If you just plug in 0 right now for the limit, like just via substitution, you will get 0 over 0, which doesn't make sense. So what we need to do is expand that binomial x plus h and so cancel out the terms x squared. So there's a positive x squared and a negative x squared that can cancel out. You can also factor out an h, cancel out an h in the numerator and denominator to get you that the f prime of x function is equal to the limit as h approaches 0 for 2x plus h. Now you can do the substitution for the limit, and you'll see that the slope of the function x squared is equal to 2x. The slope of the function f is defined to be 2 times the input. So then if we plug in 1 here for our f prime, we're going to get 2. Our slope is 2. Alright, so let's do that again for the function f of x equals x cubed. Apply the limit, expand our exponent, cancel like terms, and factor out an h. Make our substitution for the limit, and we'll get that f prime of x equals 3 times x squared. So this means that the slope of our function f is defined as 3 times the square of our input. Alright, and if we plug in 1 here, we'll see that at point 1, 1, our slope is 3. Alright, so what if we wanted to find the slope of a more like tedious function? Given the function f of x equals 5x squared plus 3x plus 7, how can we find f prime of x? Are we seriously going to take the limit of this, expand, cancel like terms? That seems very tedious for no reason, and no mathematician or nobody trying to solve this derivative is going to do it that way. So then, if not, then how do we do it? Well, let's compare the two functions we differentiated using the limit definition. F of x equals x squared and f of x equals x cubed. So when we took the derivative using limits, we got that the slope of f is equal to 2x, and for our other function, the slope of f was equal to 3x squared. So what do you notice here? What is the relationship, or what is the pattern? Well, if you're very observant, you'll see that there is a pattern. For a function defined to be as x raised to the power n, the slope of that function is equal to the power times x raised to the same power minus 1. And this is called the power rule. So take a screenshot of this or a picture, jot it down in your notebook, whatever. This is a very important rule. It is the first rule that comes out from the limit definition of a derivative. So let's use the power rule on these three different functions here. So if I wanted to take the derivative of x, x to the 5, or 1/2 times x squared, how might you do it? So pause the video, take a second, and go ahead and do that. Alright, so hopefully you got either 1, 5 times x to the 4, and 1/2 times 2x, which is x. So I just want to kind of go over the first one here. If you're differentiating x with respect to x, you're looking at the change of x with respect to x, right? So that means delta x over delta x. And that's just 1 because there's going to be the same numerator and denominator there when you're looking at change. Also, you could use power rule, bring down the degree. We know a degree of a variable is always 1. So subtracting 1 by 1, you will get 0. So that's obviously 1. Since anything to the power of 0 is 1. Alright, moving on. We come to our second rule, the constant multiple rule. If you differentiate a constant times a function, you can essentially pull the constant out of the differential operator and just do the constant k times the derivative of f of x. And that's going to be equal to the constant times the derivative of f of x. Yeah. So for example, let's look at 3x squared, which was the derivative of x cubed, and we're differentiating again. So what can we do? Well, we can pull 3 out of the differential operator, so we'll get 3 times d dx of x squared. We know that the derivative of x squared already is 2x, so we'll do 3 times 2x to give us 6x. Alright, next rule, the sum rule. So the sum rule reads, if you take the derivative of a sum of functions, you can differentiating term by term. Basically just means that you're taking the derivative individually and you're adding them up. So an example would be, take the derivative of x squared plus x, and you will get the derivative of x squared plus the derivative of x. And of course that is equal to 2x plus 1. Alright, now the difference rule. I call this the bogus rule, the fake rule, the whatever rule, because it's basically the same thing as the sum rule, but the g of x here has a constant multiple of -1. So this isn't really a rule. I don't know why they included it, but if they're going to get lazy, I'm going to get lazy. So the example here is just the same as the previous one, just x has a coefficient of -1 instead of 1. So the answer will be 2x minus 1 instead of 2x plus 1. Alright, moving on. Product rule. If you differentiate a function f times a function g, you will get that it's equal to the derivative of the function f times the function g plus the function f times the derivative of g. Alright, so this is a note. This is something you're going to have to memorize anyways, but the derivative of the function e to the x is always e to the x. So I'm going to use that here in my example. If I differentiate x times e to the x, I'm going to get e to the x plus x times e to the x, and that is via the formula for the product rule. Right, now the quotient rule, very similar to the product rule, but instead you have subtraction here. So it'll read f prime of x times g of x minus f of x times g prime of x all over gx squared. So that is the formula for here. Here is the example. So if we take the derivative of e to the x over x, it will read x e to the x minus e to the x over x squared. And this again is just via the formula. You're just plugging and chugging for these derivatives. Alright, now the chain rule. The chain rule is a rule that confuses students a lot more, including myself when I first learned it. So if we're taking the derivative of a function f with an input that is a function g, then that is equal to the derivative of the function f with input g times the derivative of g. So I wrote an example here. We'll go ahead and look at the note. We're saying that f of x is equal to e to the g of x and g of x is equal to x squared. If you do the plug-in for fog or f of g, you'll get that it's e to the x squared. So then we're taking the derivative of e to the power g of x. And of course, that is just going to be e to the power of g of x, right, from the previous note that we left. So then we get e to the power of g of x, that's e to the x squared, times the derivative of g of x right here. And that's going to be 2x, right, because the derivative of x squared is 2x. So that's how we do that. But I want to write down one more example here. And it's going to be sine 3x. If you want to differentiate this, how do you go about it? Well, you don't know the derivative of sine, but I'm going to leave another note here. Note that the derivative of sine with input x is equal to cosine of x. So just note that for now. So if the derivative of sine is cosine, then this is equal to cosine with input g of x, right? Because g of x in this case is 3x, times the derivative of g of x. So if g of x is 3x, then that derivative is obviously 3. So this would be that answer. So these are the two answers we got using the chain rule. So again, it might look difficult, but it's pretty easy. Alright. So this is a derivative cheat sheet. These are all the derivatives that you're going to need to memorize to be successful in differential calculus in AP Calc AB. So starting off with this one, I already noted it before in like one of the examples. The derivative of e to the x is always e to the x. Similarly, the derivative of a constant a to the power x is equal to that base a of x times ln a. So this kind of feeds into this definition here. If a was equal to e, we'll get that the derivative of e to the x is equal to e to the x times ln e. Ln e is 1, so that ends up just becoming e to the x. And that's how we have the definition for that derivative over there. All right, moving on. The derivative of ln x is 1 over x, okay? And similarly, the derivative of log base a of x is equal 1 over x times ln a. And again, this has the same kind of like feeder for that definition. Because for base e, that's what ln is. Ln e obviously is 1, so you get 1 over x. Now, these aren't really things you need to memorize, but they're good time savers. Because you will come across a lot of chain rule functions where there will be in square roots, and it's just good to know that this derivative of a square root is 1 over 2 with square root in the denominator as well. So that one you might need to memorize. And the derivative of a constant is always 0. This is by power rule. Both of these are by power rule, so should I write that down? Power rule. Both of these from power rule. All right, now the trig functions. I gave this one earlier. The derivative of sine x is cosine x. The derivative of cosine x is negative x. The derivative of tangent x is secant squared x. The derivative of secant x is secant x times tangent x. The derivative of cosecant x is negative cosecant x cotangent x. And the derivative of cotangent x is negative cosecant x squared. Moving on to the inverse functions, we know that the derivative of inverse sine x, or the derivative of arcsine, is equal to 1 over the square root of 1 minus x squared. Okay, now the derivative of cosine inverse, or arc cosine, is the same thing but negative 1 coefficient. Alright, the derivative of arctan of x is equal to 1 over 1 plus x squared. Obviously, this is addition. You can move it around however you want, but you'll probably mostly see it like 1 over 1 plus x squared. Alright, now this might look like a lot to memorize, but it isn't, and I'll tell you why. For every trig function that starts with c, a negative is going to come out. So let's look at cosine x, cosecant x, cotangent x, cosine inverse x. All of these have a negative in front of it. And also, another pattern, differentiating a tangent function will give you a reciprocal function squared. Differentiating a cotangent function will give you the reciprocal function squared. But of course, since this has a c, you get the negative out of it, okay? And for the inverse functions, obviously you can see these are very similar. The pattern should be apparent to you. But anyways, that is all I have. That is basically everything to get you started on differential calculus. I would like to thank all of you for watching the video all the way to the end. If you have any questions, concerns, or if I did something wrong or something isn't clear, please leave a comment down below. Also, if you're interested in more videos, like integration techniques, etc., the rest of the AP curriculum, please subscribe and like this video to let me know. Anyways, have a great day, and I wish you luck on your journey.